The massive explosion is an idea that has laid out the framework for deciphering the universe. It explains the support of current cosmology in Einstein's view, speculation also known as coarse-reading cosmology. The enormous explosion, the very first moment of the universe's development, points to the emergence of energy and the presence of all matter. This occasion occurred approximately 13.8 billion years ago and prompted the colossus universe we can see today. Albeit recent advancements in cosmology indicate that most likely, the colossal explosion was not the very beginning. Rather, there could have been a stage prior to the explosion, an earlier phase important in shaping the universe. This pre-period is referred to as cosmic inflation. One of the most fascinating contemporary ideas in cosmology suggests that before the intense heat of the Big Bang, the universe experienced unimaginable, rapid expansion. During this time, the universe duplicated its size at a shocking rate. To illustrate how absurdly fast this extension was, assuming the universe began smaller than an atom, it would have grown to become unfathomably larger than the entire visible universe within a minuscule fraction of a second, around 1/4,000,000th of a second. This inflationary stage lasted only a short time, but it played a crucial role in forming the universe. After the inflationary phase ended, the energy driving this expansion was released into the universe, warming it and creating the particles of matter that make up everything we discover today. There are many ways in which inflation is seen as a precursor to what we call the Big Bang, while the hypothesis of inflation itself, though widely used in cosmology, still faces many unanswered questions. For instance, why did inflation begin? What brought it to an end? How long did it last? These are all open questions in cosmology, and addressing them is crucial to better understanding the universe's beginning. Prior to inflation, the universe was in an extraordinarily dense, small state, a region frequently referred to as a singularity. From this singularity, evolution began, ultimately leading to the formation of atoms, stars, and galaxies. While the Big Bang theory provides a powerful explanation, modern cosmology proposes an even more complex picture. Some theories suggest that before the Big Bang, the universe underwent a phase of inflation, doubling in size at a rate faster than 1/1,000,000th of a second. The fuel for this brief expansion came from a bizarre energy structure, possibly originating from the void of space. When inflation ended, this energy transformed into particles, warming the universe and triggering the conditions we refer to as the Big Bang. Interestingly, the inflationary stage itself was empty and cold, yet it laid the groundwork for the matter we see today. One of the more current theoretical considerations is the concept of eternal inflation, the idea that expansion did not stop everywhere at once. Instead, it ended in some regions while continuing in others, creating a variety of pocket universes, each potentially with its own physical laws and constants. This is where the concept of the multiverse emerges. Our universe may be just one of many, or even an infinite number, of universes. If this is true, it could explain why our universe is so well suited for life. Every possible configuration of physical laws could exist in different universes, and we just happen to live in one ideal for stars, carbon, and the chemistry of life. While multiverse and eternal inflation theories remain speculative, the theory of inflation itself is based on observational evidence. The strongest support comes from the cosmic microwave background radiation, CMB, the oldest light in the universe, emitted about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. Since then, this light has traveled across the cosmos. By studying it, cosmologists can essentially take a baby picture of the universe. The CMB reveals details about the early universe's structure, and its slight temperature variations are in line with predictions made by inflationary theory. One of the most important sources of this evidence was the Planck satellite, operated by the European Space Agency. It captured high-resolution images of the CMB, showing subtle fluctuations that matched inflationary predictions, supporting the idea that inflation is not just a speculative theory, but a significant component in our understanding of the universe's origins. To fully understand the Big Bang and what came before it, cosmologists aim to unite two major theories: Einstein's general relativity, which describes gravity and large-scale structure, and quantum theory, which governs the behavior of atoms and particles at the smallest scales. A unified theory, sometimes called quantum gravity, would allow scientists to explain both the vastness of space and the conditions that triggered the Big Bang. Today, the majority of distant objects we can see are approximately 47 billion light-years away, meaning the observable universe is about 94 billion light-years in diameter. This might seem odd, considering the universe is only 13.8 billion years old. How can the universe be larger than the time it would take for light to travel? The answer lies in the fact that space itself has been expanding over time. As it expands, the distance between objects increases, creating regions that are farther away than light could have traveled since the Big Bang. Most researchers agree that while the observable universe is immense, the entire universe may be infinite. The observable portion is limited only by the time light has had to travel since the Big Bang. Beyond that, there may be regions of the universe we will never see. If the universe truly is infinite, it may have no external boundary, and thus no outside. In such a case, it would make little sense to speak of a before the universe, since time and space as we know them would have originated with the universe itself. Space, which is one of the properties of the universe, so the potential for the past most likely. The universe won't have any physical meaning in the same way that it began. The origin of the universe is the focus of amazing concentration. So, too, is its inevitable conclusion. The best available gauge is that the universe will continue to grow. This is always anticipated. Dark energy is a strange phenomenon, which is responsible for the universe's extension in order to move quickly. Prior to the emergence of dark energy, scientists believed that the universe's extension would eventually reduce due to the pull of matter's gravitational force. Indeed, there was even a possibility that the universe might stop expanding and begin contracting, resulting in a major crunch. But dark energy appears to be tearing the universe apart more and more swiftly. If this rate of acceleration continues, the universe will never stop expanding, eventually getting to a point where galaxies float so far apart that they separate themselves from one another. In this circumstance, the universe would transform. Stars would wear out, cold, lifeless, and exhausted. Matter in our worlds would drift apart and would eventually rot, as this is known as the major heat or freeze death of the universe. The story of everything, from the massive explosion to one of the most improbable outcomes, is an important and intricate story in science. Despite the fact that we've gained an extraordinary amount of knowledge about the places where the universe is based, on the theory of expansion, as well as the study of the extensive microwave background, numerous inquiries remain unanswered. The reason for expansion to begin and end, what lies beyond the visible universe, do we have a multiverse, and how many additional universes exist? As the research continues to focus on the universe by employing new ideas and hypotheses that connect quantum mechanics together with general relativity, we will doubtlessly gain a deeper understanding of these mysteries. The journey to comprehend the mysteries of the universe continues in all disclosure, and helps us get closer to taking note of the severe inquiries regarding our existence. The study of the structure and beginnings of the universe is more than just a logical attempt. It likewise brings philosophical inquiries regarding the reality of our presence and position in the universe. One of the most important topics of cosmology, of interest, is the accepted characteristics of dark matter, which generally makes up 27% of the mass and energy of the universe. Dark matter, unlike normal matter, does not absorb or reflect light, making it both invisible and observable only by means of its gravitational consequences for the matter that is obvious. This is essential for understanding dark matter and for understanding the development and evolution of universes. Research and perceptions have provided some knowledge of the properties of dark matter. However, its specific nature continues to be difficult. Only a few candidates have been suggested, including massively interfering weakly interacting particles, axions, WIMPs, and other alien particles. However, there has been no immediate discovery of dark matter particles. The search continues through a mix of astrophysical and terrestrial tests, perceptions, and activities that serve as a model for how the vast universe is affected by dark matter in its construction on a grand scale. Dark energy is another important area of research. Energy is the key driving power behind the acceleration of the universe's expansion. Dark energy accounts for approximately 68% of the absolute mass and energy content of the universe. Its revelation was unexpected and prompted a number of hypotheses, one of which is the dynamic and cosmological constant. The study of the essence, for instance, is necessary because dark energy determines the extreme fate of the universe. Researchers are focusing on the universe, pertaining to its effects on cosmic structures and trying to determine whether it remains consistent over time or progresses. Despite the existence of dark matter and energy, extensive investigation into structure development provides significant insight into the universe's collection of experiences and opinions about the incredible, vast groups and systems organization. Fibers have demonstrated how matter clumps together, prompted by the influence of gravity, forming the baffling patterns we currently see. Supercomputers are used for reproductions, aiding specialists in comprehending how these structures developed over billions of years and continue to advance. Additionally, astrobiology converges with cosmology as scientists attempt to determine the conditions necessary for life. They are looking for exoplanets beyond Earth, planets that orbit stars outside of our solar system. The group of planets has grown with thousands discovered over time. A few of these exoplanets are found in their habitable zones of their stars, where fluid water may exist and potentially benefit from the right conditions. By taking into account these distant worlds, scientists hope to learn more information regarding life's potential in different locations in the universe and the things that make a place friendly to life. Finally, the central position of cosmology's material science cannot be overstated. The mission for a unified theory that connects general quantum theory and relativity continues to confront physicists. Theories like string theory and quantum gravity intend to link these 2 points, which provide clarification for unusual phenomena like black holes and the beginning of the universe. Innovation drives our capacity to recognize and comprehend the vast peculiarities of space. Space telescopes like the James Webb enable new ways in which we can interpret the cosmos by offering amazing attention to detail in distant systems and cosmic events. Each revolutionary perception brings us closer to unraveling the enigmas of the advancement of the universe's arrangement and extreme destiny. An investigation into the universe as a complex web of logical demands and philosophical thought. From the main forces that make huge plans for the search for extraterrestrials, our investigation is a way of life, an illustration of human perseverance and enduring fascination with the cosmos. As we try to respond to these important questions, we gain a greater, profound gratitude for the incomprehensibility and complexity of the universe.